Well, welcome to the start of the unit called chemical bonding. And we've been kind of building towards this since we first started studying atoms. So just kind of set the stage here. We described what atoms are and what's inside of them. To put it very briefly, we've got a nucleus, which contains protons and neutrons. And we've got electrons, which are outside the nucleus in these, we think of them as orbits called energy levels. Now, that's not a perfectly accurate picture, but it's a pretty good model for us to use at this level. So in the last chapter on the periodic table, we described how atoms aren't necessarily happy until they have a full outer energy level, a full outer level, which for most atoms means they want 8 outer electrons. We often call them valence electrons. Now, there are a few elements that are okay with 2. The ones that only have 1 energy level can't hold any more than 2. But for the most part, we think of full meaning 8. Okay? So now here's the next step in the progression. In order to acquire 8 electrons, you either gain or lose, or as we'll learn about later, share some electrons with atoms that are around you. And in doing that, you form kind of this, we call it a chemical bond with that atom so that both atoms are kind of happy near each other, all right? So that chemical bond is what we're describing in this particular unit. All right, so let's start with just a definition or a description of what a chemical bond is. It's the attraction between atoms. Make sure, by the way, you're listening to the audio of this, not just using the captions or watching me write. This is very important to hear the context as well. The attraction between atoms due to exchanging or sharing electrons. Again, that exchange or sharing is all because atoms are trying to fill their outer energy level, okay? So there's 3 different kinds of bonding, which I'll describe in part 2, but we're going to look at probably the simplest one to describe is called ionic bonding, okay? So to describe ionic bonding, we first need to know what we mean by an ion, all right? So an ion is atoms which have acquired or lost electrons. So again, in the last unit, we talked about which ones are going to want to acquire some more or gain 1 or 2 or maybe 3, and some atoms that want to lose 1 or 2 or 3. And once they do that, we don't call them an atom anymore, okay? They are now a charged ion, all right? So ions have a charge. So it's a very important property of the ion based on electrons gained or lost. All right, so again, atoms turn into ions when they gain or lose these electrons. So I'm going to show you, using the Lewis dot model that we learned in the last unit, I'm going to show you how we represent what happens when an atom turns into an ion, okay? So let's start with the element sodium. So I'll get my periodic table here. Sodium has kind of an odd symbol here. It's Na. You wouldn't necessarily think it would be. A lot of these names are based on the old Latin names. Okay, so sodium is a metal, and it is in group 1. So what we do when we represent this is we draw its Lewis dot model like that. That's the neutral atom. That's an atom that doesn't have a charge on it. It's got as many plus protons as it has minus electrons. That's why we call it neutral. But what happens is, because it's trying to get rid of that electron to have a full outer energy level, its ion symbol has no dots on it. Okay, so metals will lose all of their dots. Those are those outer electrons. But what we do then is we write the charge that we end up with on the atom. Now, here's what throws people off. When metals lose their electrons, they're losing negative charges. They're not losing positives, they're losing negatives. So they always end up having all of their positive charges left, but not as many negatives. What that means is they have more positive protons than they have negative electrons. So they become a positive ion. Sodium becomes a positive 1 ion because it lost 1. How about a magnesium? Magnesium is in group 2, right next to sodium. And so it will want to lose 2 electrons. And therefore ends up having 2 more protons than electrons. Not because it gained protons, because it lost its electrons. So it has a charge of +2. Okay? Now, what happens with nonmetals? Well, let's take a look over here. How about chlorine in group 17? That means it has 7 outer electrons. So we'll draw it 7. And put 2 on each side, but 1 on one of the sides. And now, instead of losing, it's not going to lose 7. It's much, much easier to acquire 1 more. And so we actually have 8 dots on the non-metal ion symbols. Takes on that 1 extra electron that it gets from somewhere. And in the process, because it now has more negative charge than when it was neutral, it has a -1 charge. Okay. Similarly, next to it, we've got sulfur. Sulfur is too short of a full outer energy level. So it's got 6, like that, for example. And when it acquires those 2 extra electrons to fill its outer energy level, it becomes a -2 charge. So you see what we do? We put the extra dots on the nonmetal ions, and we put the charge based on how many additional electrons they acquired. Okay? So those are the Lewis symbols for ions. So now on the next page, let's describe more specifically what we mean by an ionic bond. I talked about chemical bonds in general. Now the ionic bond is the attraction between a metal ion and the nonmetal ion which took its electrons. So let's think about this kind of together. We've got these sodium atoms, for example, that are trying to just get rid of 1 electron. Well, here we've got this chlorine atom that's trying to get an electron. It's like a match made in heaven. So when the sodium atom gives away an electron and the chlorine atom acquires that electron, they are forever bonded together by this mutual exchange, and we call that attraction an ionic bond. Okay? So there's a lot of the background, some of the terminology. Now we're going to get to the skill that I want you to have, and that is really 2 things. I want you to be able to write the formula for an ionic compound and the name for the ionic compound. Okay? So first, let's describe what a compound is. A compound is the result of the bonding between atoms. It's a new material. With different properties. Than the elements. So every time this bonding happens, you form a new substance. It looks different. It behaves differently. It's got totally different characteristics or properties. Okay, that's what we call a compound. And I'll be describing these compounds as we go. So you're going to write the formula. It's like the recipe, if you will. And you're going to name it. Okay, so let me tell you what's involved in each of these, and then we'll do some examples. Okay, to write the formula, step 1, you write the metal symbol. This is right off the periodic table. And then the nonmetal. Oops. It's always in that order. The metal first, then the nonmetal. That's why it's important to know which are which on the periodic table. Step 2. If needed, write small, we call these subscript, small numbers, to show how many atoms are needed in the exchange. Talking about exchanging these electrons from metal atoms into the nonmetal atoms. Sometimes it works out great. Like my sodium and my chlorine. Sodium had 1 to give away, and chlorine was looking for 1. Well, that doesn't always work out so beautifully. Sometimes there's a mismatch. And I'll show you then how we use these little numbers to show how many of everything we need. Okay? So I'll do a few examples in just a second. But let me describe the naming. So every substance has a different name. So the elements have names, just what we see on the periodic table. But when we put those elements together, we have to name them after what elements they're made from. So for ionic compounds, we name the metal first. Followed by the nonmetal. But a little change here, changing its ending to the letters IDE. Sorry, there we go. So ionic compounds almost always end with the letters IDE. You'll recognize some of these. You've heard of fluoride because it's stuff that they put in toothpaste and water to keep our teeth healthy. Fluoride is the ion made from fluorine. So we just changed fluorine to fluoride. You've heard of sodium chloride before. I was talking about that one earlier. Sodium chloride is the fancy chemical name for the compound we call salt usually. Chlorine changes its name to chloride. Okay. You've heard of oxide. Well, when oxygen is involved in ionic bonding with a metal atom, we change the name from oxygen to oxide. All right, so here are the endings on this little chart just for your convenience to look at. All right, so let's look at a few examples of how we write the formulas and then write the names. Okay, so I'm going to do 4 examples for you. And again, like I said a moment ago, this is the main skill that I want you to have. All right, so tune into this because this is what your first worksheet will look like, your quizzes, tests, things like that. All right, so we're looking for a formula and a name, and all I'm going to give you is the metal and the non-metal that are involved. We can always make an ionic compound from a metal and a non-metal. All right, so let's suppose we start with potassium and chlorine, and those are hanging around each other, and they decide to form an ionic compound. Why? Because neither one of them is happy right now. Let's remember what we've got. Here's potassium over here. That's the symbol K. It's in group 1, so it's got 1 outer electron. So I recommend that you draw a little Lewis dot diagram for potassium. And then I was mentioning chlorine a moment ago. It's in group 17. So it's got 7 outer electrons. Helps to have that visual in front of you. Okay, so here's a case where I think most people can see this. This one electron that potassium is going to try to get rid of would be great over here in this chlorine atom. And then both of them become an ion, a potassium ion with a positive charge and a chloride ion with a negative charge. Okay, so then the formula is KCl, just a little gap in between them. And I mentioned that you might want to put a small number in, but if you need only one of each, you don't put any additional numbers in. Okay, so we kind of understand it that there's just one of each. That's a common mistake. People throw ones in, but we don't do that. The name, you name the metal ion first, potassium, and then you name the non-metal ion, changing its ending. Now this one you do put a little space in because these are two words, kind of like you have a first and last name. It's sort of like its first and last name. So potassium chloride is the name of that compound, okay? Now this stuff, if you could see it, it's a white, kind of a crystal-y stuff. It looks nothing like potassium metal, which is a shiny, hard substance. It looks nothing like chlorine, which is like a greenish yellow gas. The properties, the characteristics are totally different of a compound compared to the elements that make up that compound. That's an important point I want you to have. Okay, now let me show you one that's a little tougher. And I'll show you a strategy using your little papers that you used for the lab. So let's say we want to do this with magnesium and chlorine. Okay, so magnesium, I was mentioning this one a little bit ago. It's got 2 outer electrons. And chlorine, same as above, has 7 outer electrons. Okay, you have those in front of you. So the formula will be Mg, a little bit of a gap, not a big space, and then Cl. Now we need these small subscript numbers. Why? Because notice that if magnesium is trying to get rid of 2 electrons, it cannot give them both to a chlorine atom. Chlorines don't want 2 more electrons, they only want 1. So poor magnesium's got 2 to get rid of, and he doesn't have enough chlorines to give it 2. So we bring in another chlorine. So let me show you how these little papers are helpful. We could represent the magnesium atom as this, trying to give away 2 electrons. But the chlorine does not look like that. This is what a chlorine looks like. It's only willing to accept 1. So if we kind of pair these things up like this, the chlorine's happy now, but the magnesium's not. So we bring in a second chlorine to accept that other electron. Now we see we need 2 of these chlorines for every 1 magnesium. So what we do is we put a 2, that's a small number, just after the chlorine. We don't put anything after the magnesium because if we only have 1 of something, we just leave it as it is. So that is its formula for the ionic compound. And what is the name? The name is magnesium chloride. You don't have to worry about the numbers on the name. Just change that ending of the nonmetal to IDE and you're good. Okay. How about calcium and sulfur? Calcium, that's a Ca. It's in group 2, a lot like magnesium, right? So it's 2 outer electrons. Sulfur, we haven't seen sulfur yet today. Here's sulfur. Group 16, they have 6 outer electrons. Aren't you happy you learned about the outer electrons? All right, let's think about this formula. So the metal symbol goes first. Remember, always use a lowercase on that second letter. A little bit of space, not too much, and then the S. But how many of each? Now, people will mix this up too. Notice that calcium's trying to give away 2. So, a lot like magnesium, right? But we've got sulfur now that's willing to accept 2, kind of like this guy. Notice I don't need any additional ones. 1 of each is perfect. So I am not going to put any subscripts on this because I don't need multiple atoms. See how those papers kind of help you out. And what is the name? The name is calcium sulfide. By the way, you will see sulfide written with a PH instead of an F. It doesn't matter to me, but our periodic table writes it with an F. Okay, and the toughest one, not a hard one, but it's just the toughest one that we have, aluminum and oxygen. So aluminum. Aluminum is kind of an oddball because he's way over here, right? You would think maybe he's a metalloid, but aluminum is way too much like a metal to be considered a metalloid. He's actually one of the best metals here. Real common around, right? So 3 outer electrons being there in group 13. And oxygen. Oxygen's right above sulfur, so 6 dots, just like the sulfur had. Now this one will sometimes twist your brain into knots a little bit. How do we make this work when we've got aluminum trying to get rid of 3 electrons, but every oxygen atom can only take 2? This is one of the main reasons why I made these papers. Okay, let me clear a little space here. So what's an aluminum? An aluminum trying to give away its 3 electrons. That's this guy right here. So do you notice, here's a sulfur that's trying, or sorry, this is an oxygen, right? An oxygen is only trying to take 2 more. So there's no way that 1 of each is going to work. Well, what if we had another aluminum? Like that. Well, certainly we're going to need additional oxygens to take all those electrons. We're getting closer. I just need one last one. Here's another oxygen coming into play. There we go. A total of 6 electrons being given away by these 2 aluminum atoms, and a total of 6 being accepted by the 3 oxygen atoms. So now count this. 2 aluminums, 3 oxygens. So what's the formula? Al2O3. Okay. And what's the name? Aluminum oxide. Aluminum oxide. All right. There's a lot there. I'm going to recommend when you're working through worksheet number 1, this page, if you kind of go back to where I started this page, listen to this description again. Sometimes the first pass through isn't enough, but that's why I put these things on video. So if you need to go back, get a little help, you can. I've even made an extra video just for this first worksheet. That's a little different than this one because sometimes you just need to hear it again with some different examples, okay? So, all right, we're going to do it for this part. I know this is a long one, but you learned a lot in the process of these 24 minutes or so. So hopefully that's helpful. Go back and replay the parts that you need to, and then move on to the next step. Thanks for watching.